Let's see optical instruments. In this article, we'll see how our eyes they see things, they magnify things, simple microscope, compound microscope, telescope, all these things. And basically, we are dealing with lenses. All that we have learned in lenses and all that will be useful for optical instruments. First thing, how do we or our eyes measure size of an object? We have an object of height h. This object is AB. And this object is at a distance of D from our eyes. Then the way we perceive size of an object is not by looking at h or by looking at D. Instead, the angle which this object makes, the angle which this object makes on our eyes decides size of an object. Which means if I place an object somewhere here and let's say its height is h dash and it is at a distance of d dash. This is d dash and this whole thing is d. You're looking at this second object a dash b dash. If you ask this observer, then he will say that both these objects they are of same size because they both subtend same angle on our eyes. Now you can see that h, it's a bigger object than the h dash. Reason being, you're looking at this part from this side. For an observer, let's say if you go for theta of this object and this object, then for you base for h and h dash is what same, and therefore larger the object, greater will be the angle for an observer looking from this side. But if you ask him, he will say that both h and h dash they subtend same angle and therefore they are of same size. So although h is greater than h dash, theta is same for this observer and therefore he finds that both these objects are of same size. Now this theta we calculate in terms of tan theta. What is tan theta? Tan theta is h upon d or h dash upon d dash. And if we say that angles are small, then this theta, tan theta, it can be approximated with what? Theta. and therefore from now on size of an object will be decided by theta, which is h upon d. If we can increase theta, that means we are magnifying an object. What I'm saying is, if you place this same object AB closer to the eyes, not h dash, same object, then as it comes closer, look here, as it comes closer, it is at this position, this is h, this distance is d, that's the angle, this is theta. Now, suppose you move this object at this position. Same object, but at somewhat less distance. Let's call it D2. Let's call it D1. Then, as it moves to this position, angle subtended by the object on our eyes is theta 2. This is theta 1. You can see that theta 2 is greater than theta 1. Although length of the object is same for you, for this observer, this same object, as it comes closer, we say that we are magnifying the object. We see as if its size is increasing. We can see more detail in this object. So, closer you place an object to your eyes, larger will be the size. Now, there is a limit. If you keep on decreasing this distance, after a point, size will increase, but you will lose clarity. Why does it happen? Because eye lens, it won't be able to focus rays coming from the object at the retina. So, if you bring this object much closer, then you can see that size is increasing for him. But after a point, as you bring it closer, eye lens, it won't be able to focus light rays coming from the object at the retina, and therefore clarity will be gone. So we have developed a distance d, which we say that is the closest you can place an object and you can still see it with proper clarity. This distance is capital D, which is approximately 25 centimeter, and it varies with person to person. For this D, angle which an object makes theta naught. This theta naught is the maximum angle which we can see without any optical instrument, that is without any microscope, simple or compound. If I bring it closer at 25 centimeter, when I keep it, this is the maximum magnification which I can see with clarity. If I bring it further close to my eyes, size will increase, but I won't be able to see further details into it. So this theta naught is the maximum angle, and this maximum angle you can see is h divided by capital D. Write down few points. Our eyes do not see do not see height or distance of an object, height or distance of an object. Instead, it's the angle which an object forms on our eyes gives us perception of size. Gives us perception of size. A very basic example will be that if you look at disk of moon, and you know that you can cover that entire disk of moon with a 1 rupee coin. If you place 1 rupee coin at appropriate distance, then you can cover the entire disk of moon. Which means what? For you, size of moon and size of this 1 rupee coin, they both are what? Same. Your brain perceives them as if they both are of same size. Why? Because they both are subtending same angle theta. Now continue with the statement. For example, in figure 1, both objects AB and A dash B dash, will appear as if they are of same size, to the observer, shown in the figure. To increase size of an object, therefore, we must bring it closer to our eyes. But after a particular point, called near point, it becomes difficult for eye lens to focus rays coming from the object at the retina, and therefore, although apparent size increases, but we lose clarity. Distance of near point from our eyes is called least distance of distinct vision. And it is approximately 25 centimeter. When an object is placed at near point, its apparent size is maximum its apparent size is maximum, and is represented by theta naught, and is represented by theta naught inside the bracket without using any optical instrument. Without using any optical instrument. Note down this much. Now let's see how a simple microscope, which is nothing but a convex lens, helps us in magnifying size of an object. So write down simple microscope. Simple microscope. We have a convex lens. This is the optical axis. We have an object. Its height is h. And if you remove this convex lens, then angle which this object subtends at this point. Now this point represents position of your eyes. This is the position of your eyes. We keep our eyes close to the optical center of a lens. So from now on, when we say that angle formed at the eyes, that means at the optical center of simple microscope. Now, if you remove this lens and you place an object at a distance of d, then the angle which it subtends is theta. This angle is theta. Now, when you place this simple microscope, something like this happens. This is the second ray coming from the object, and its refraction is going to happen. Now learn how to draw a ray diagram. This is the second ray, this is the first ray. Their intersection gives us what object? Now you will first produce this line backwards like this. Then you will take an image at any random position behind H. Learn how to draw a ray diagram. It's a virtual object, virtual image. Its height is H dash. Now, once you have drawn this image, from the top of the image, join this point. and then show this thing in terms of broken line. Now, this ray you can see is passing from the middle portion, which you know behaves as a thin glass slab, and therefore this ray goes straight, and this ray is coming like this. Now, you know that aperture size is also kept very small, and therefore this and this, they both will be collected by eye lens. This ray, in the ray diagram, it appears that it's moving above your eye lens, but remember this and this, they both are being collected by the eye lens. So when you go for this, it's coming from this point. What is this point? This point is A dash. This is B dash. This is B, and this point is what? A. And your image in this case is being formed at D dash. Now, if I say that this theta is greater than theta naught, try to understand. If I say theta is greater than theta naught, then you know that our brain, our eyes, they will perceive as if we have magnified the thing. But if you don't have the lens and you place your object at some distance which is less than capital D, then theta definitely will increase, but you will lose what? Clarity. Now, what we have done, we have placed a convex lens, and because of the convex lens, instead of looking at the object, we are looking at its image, which is at a distance of D dash, and this D dash is greater than or equal to capital D. This D is less than capital D. So, for eyes, this is the object. Remember, this is the object, this is the image, but for eyes, there is nothing at AB because this lens makes AB appear at A dash B dash. So when you place a convex lens in front of your eyes and you look at an object, you're not looking at the object, you're looking at the image. So for the eyes, this is something which I called object, but remember it's an image. For eyes, this is something which is at a distance of D dash, and D dash is greater than or equal to what? Capital D, and therefore everything is okay. This theta, you can see that since small d is less than capital D, is automatically greater than what? Theta naught. But if I remove the lens, if I remove this lens, then I find that size is magnified, but clarity is gone. Once I put the lens, you see that H dash, it is also subtending same angle theta, but for our eyes, its position is at D dash, which is greater than what? Capital T, and therefore we will see a magnified image with proper clarity. I hope you understand how magnification works. We are trying to fool our eyes by using this convex lens. Now, the way magnification is defined for microscopes is this: M is theta divided by theta naught. This M is called magnification for a microscope, simple or compound. Theta naught, you already know. What is theta? Theta is angle formed by the image on your eyes or at the optical center of simple microscope. When we'll go for compound microscope, in compound microscope we have two lenses. One which faces object is called objective, we'll see that. And the one close to our eyes is called eye lens. This will work as an eye lens in that case, eyepiece. So remember, eyes are at this position close to the lens, and therefore when we say that angle formed by the image on your eyes at this position is same as if it is at this position, which you see as what? Theta. So write down the formula of magnification. Magnification is theta upon theta naught, and in that write down what theta is, because theta naught is something you already know. Theta is angle formed by the image, angle formed by the image inside the bracket or final image. When we deal with compound microscope, there are two lenses and therefore there will be two images, one intermediate and one final. So theta is angle formed by the image inside the bracket or final image at our eyes. Which is same as at the optical center of simple microscope, or in case of a compound microscope, at the optical center of eyepiece. We'll see compound microscope later. As of now, let's concentrate on this part. So now we know that how to magnify things. What is theta in this figure? Theta is coming h upon d, which is same as h dash upon d dash. Our eyes, now they are not looking at AB, they are looking at A dash B dash. So the angle subtended by A dash B dash is basically h dash upon d dash. But h dash upon d dash is same as h upon d, tan theta, perpendicular upon base. So this is theta, which is h upon d. Now, in m, when you put it, what is theta naught? H upon d. What is theta? Technically, we should have h dash upon d dash at this position. Angle formed by the image, and that angle is what? H dash upon d dash. But you can see that h dash upon d dash is same as h upon d, and therefore magnification is coming capital D upon D. Capital D upon D. Now, small d is less than capital D. Small d, denominator, is less than capital D. Then you can see that this magnification will be always greater than 1. It means we are looking at an object with proper magnification. Now we just need to find D. How do we find that? There are two cases we are interested in. In case 1, we say that image forms at infinity. When image forms at infinity, rays are coming parallel to the optical axis, and therefore it is easier for our eye lens to focus these rays at the retina. There is least stress or strain on your eyes. This is called case 1, when image forms at infinity. Now when you form this image at near point, in this condition, maximum stress is present on your eyes. This will be our case 2. So for these two cases, we just need to find this ratio of D and D. Write down case 1. In fact, pause the video, wrote down this much, and then for case 1 and case 2, try to find magnification using D upon D. And then come back and see the solution. So, for case 1, we are saying that image forms at infinity. Write down this. In case 1, image forms at infinity. That is, stress on the eyes is minimum. Stress on the eyes is minimum. Now what you are saying is that D upon D we need to find in such a way that H dash it forms at infinity. That's the case 1. Everybody knows when you place an object at the focus, image forms at infinity. Question is done. In case 1, what should be small d so that d dash is at infinity or d dash is infinite? So in case 1, we need to find d so that d dash it approaches infinity. You can say minus infinity, but let's talk about distances. So in distance terms, d dash is infinity, and we are interested in finding what? D. And the answer is what? D, therefore, should be equal to what? F. What is F? Focal length of the lens. Now, if you say, or if you wish, you can use this formula 1 upon f equals to 1 upon v minus 1 upon u. Focal length is what? 1 upon f. What is v? V is minus infinity. Image is being formed at infinity with sign. What is u? What is u? D. D is distance with sign. It is what? Minus d. Left side. Minus minus plus 1 upon infinity is 0. Everybody can see that d is coming f. So if d is coming f, for case 1, magnification is coming what? Capital D divided by small d. Capital D divided by f. Capital D divided by f. Result for school examinations as well as for competitive examinations. What is magnification of a simple microscope when stress on the eyes is least? d upon f. Now, if I ask you, looking at this formula, what do you think should be the focal length of the lens? Now, if you have focal length which is greater than 25 centimeter, or if you have f greater than d, then your magnification will be what? Less than 1. There is no use of it. Which means this f, if is less than d, then only you will get proper magnification. And therefore, in case 1, also remember that your f should be less than what? D. N is d by f, and focal length should be less than what? Capital D. Note down this and then go for case 2. Again, in case 2, we are interested in what? D upon D. And now we'll calculate D upon D, come back and see the solution. So, when we talk about case 2, in case 2, this object A dash B dash, this final image A dash B dash is at near point. Your small d dash is now what? Capital D. Now, you have the position of image, you know the position of image, and you just need what? Position of the object. You have the formula, you know how to use it, you can easily calculate what? Magnification. Write down in case 2. In case 2, image forms at near point. In case 2, image forms at near point. That is, stress on the eyes is maximum. That is, stress on the eyes is maximum. So in case 2, we need to find D so that capital D is your D dash. D dash, it becomes what? Capital D. And how do you find this value? Look here. 1 upon f equals to 1 upon v minus 1 upon u. What is v? This image is at capital D from the lens. Left side v becomes minus d. Minus 1 upon u. What is u? U is what? D with proper sign minus of d. And what is that we are interested in? D upon d. Let's multiply this whole thing with capital D. So when you multiply this whole thing with capital D, you get D upon F. This is D upon minus D, minus minus plus. This is D upon D. What is the magnification coming? Magnification is coming D upon small d, D upon small d, which is 1 plus D divided by F. This is magnification for the second case. 1 plus D by F. Again, it's better if you have your F less than what? Capital D. If F is less than D, magnification will be better, but this time round there is no restriction as such. Even if F is greater than D, because of this one, you will still find some magnification. And therefore, whenever we use a convex lens, we see that things are ultimately getting magnified because of this one. But if final image or that image forms at infinity, then in that case, your focal length must be less than capital D, then only you will get a magnification which is greater than 1. Hopefully things are clear. Go down everything. Let's see working of compound microscope. In compound microscope, we have got two lenses. One is objective, which is close to the object which you're trying to magnify, and the other one is eyepiece, close to your eyes. This setup is called compound microscope. What is the advantage of compound microscope? First lens, let's say it magnifies things 100 times, and second lens, it magnifies the image formed by the first by a factor of 10, and overall magnification becomes what? 100 into 10, that is 1000. So let's see the ray diagram first, and then we'll find magnification. Remember the steps for the ray diagram. Draw the optical axis. This is your objective lens. This is the object. Take a ray which passes from the optical center like this. Take another ray parallel to the optical axis. Now, this ray and this ray, after refraction, they should meet on this side. For simple microscope, rays, after they refract, they were diverging so that you could get a virtual image. Now this time round we are interested in a real image, and therefore you will try to find an intersection. This is the intersection of these two rays. Now at this position, draw an eyepiece. This is the eyepiece. Join it here. Now, this is your inverted real image. Now look at the next step. The next step, from this, join this and move it like this. At this position, you will draw an inverted image which is virtual, and therefore you need to show it with broken lines. And then from this point onwards, from this head of the inverted image, join this line and produce it forward. Same thing with this, join it and produce it. These are the rays which are collected by the eye lens. And finally, show these things as broken lines. That's how you draw a ray diagram. Remember the steps: optical axis, objective lens, that's the object. Draw this ray first, then draw a parallel ray parallel to the optical axis. It will pass from the focus of objective. Ultimately, it reaches this position. Draw your eyepiece here. Connect these two rays with the eye lens, the eyepiece lens, and then from the center, optical center of the eyepiece, join this line somewhere here, show the image, final image, and then from the tip of the inverted image, connect these two, and then these two rays, they will meet your eyes. So finally, what is happening? This ray is coming, this ray is coming, the refraction takes place, they arrive at the second lens and again are refracted by the second lens and meet eyes of the observer. This is the way you should draw the ray diagram. Now, focal length of objective is f(O), focal length of the eyepiece is Fe. If you say that magnification produced by objective lens is MO and magnification produced by eyepiece is ME, then total magnification will be MO multiplied by ME. If it produces 100 times the final image, it amplifies it by 10, by a factor of 10. Overall, this is 100 into 10, which is 1000. Now, regarding ME, we have the results. What are those results? Look at this eyepiece. For the eyepiece, you have an object, and this eyepiece is forming a virtual image of this object, which is something we have done with a simple microscope. So if you are looking at this eyepiece, it's nothing but a simple microscope. You can see that this is the object, and for the object you are getting a virtual image. And therefore this ME is something which we know already. ME, when final image forms at infinity, least strain on your eyes, for that ME was D upon F. So we'll go for two cases when final image forms at infinity, or when case 2, final image forms at the near point. When final image forms at infinity, that is case 1, and for that case 1, your ME, you know, is D upon F. Which F? For the eyepiece, this is Fe. So we'll write D upon Fe. For case 2, your ME is 1 plus D upon F. Which F? Fe. And therefore, overall magnification for case 1 is simply MO multiplied by D upon Fe, and for case 2, your total magnification is MO multiplied by 1 plus D upon Fe. Again, this eyepiece behaves as a simple microscope. When final image forms at infinity, this is the final image, this is your intermediate image. When your final image forms at infinity, magnification produced by a simple microscope is what? D upon Fe. When final image forms at near point, stress is maximum on the eyes. Maximum. In that case, magnification of a simple microscope is 1 plus d upon Fe. This is ME, and therefore we are using Fe, and you just need to multiply with magnification of the objective lens. The only thing left is to find MO. Once we have got MO, we have magnification for compound microscope. With case 1, write down final image forms at infinity. And with case 2, write down that final image forms at near point. Case 1, final image forms at infinity, and in case 2, final image forms at near point. And also write down this point that eyepiece behaves as a simple microscope. Eyepiece behaves as a simple microscope. It simply magnifies image formed by the objective lens. Image formed by the objective lens. We can also say that object is AB, your intermediate image is A dash, B dash, and your final image is A double dash. This is B double dash. Put down this diagram, and then we will find MO. Note down this much. Now let's see how we find MO. It's a convex lens, and everyone knows what linear magnification of a lens is. Linear magnification is given by V upon U. M is what? V upon U. We are interested in MO. We'll use VO and UO. So this VO and UO, they are with proper sign. Remember, distance of the object from the lens and the object. This distance is mod of UO. This much. This distance is VO. It's on the right side and therefore it's already positive. This is what? VO. This is separation between the lenses, between objective and eyepiece, L, which is called length of the tube holding both these lenses. You can always calculate this length, or you can see this length, you can measure this length from outside, L. You cannot see what is happening inside. We can always find from the outside separation between these two lenses. This is L. Now, this is magnification MO, which is VO upon UO. We need to find this. Now, what happens? This image forms very close to the eyepiece. Now, that's the reason behind using an objective lens other than the eyepiece. If you remember, with a simple microscope, what was happening? If you remove all these lenses, you place the object as close to your eyes as possible, then magnification will increase, its size will increase, but you lose what? Clarity. When we use a microscope, a simple microscope, what it does, it forms an image of this object as the image. This is the object. this image forms at sufficient distance so that our eye lens can focus these rays. Now, you want to place this thing as close to your eyes as possible, because in that case this angle you can see will increase, and as this angle increases, overall magnification will increase, and therefore we try to form intermediate image as close to the eyepiece as possible, which means your VO is approximately L. Now, if VO is approximately L, then we can find this ratio with the help of 1 upon F equals to 1 upon V minus 1 upon U for the objective lens. 1 upon F, 1 upon V minus 1 upon U. V is known. We need what? UO. You can put all these things and you can calculate what? UO. Let's put these values and you get 1 upon UO as 1 upon FO. 1 upon UO is coming as 1 minus 1 upon FO plus 1 upon VO, which is approximately what? L. So this is the value of UO, and we need what? VO divided by UO. Let's multiply this thing with VO and you get VO divided by UO as minus of L upon FO plus 1. You could have simply multiplied VO at this stage, but VO upon UO is coming minus of L upon FO plus 1. Now, this thing is approximately minus of L upon FO. Reason being, this FO is very small. Focal length of the objective lens is kept very small. If you keep FO small, then this number, magnitude wise, it will be a very large number, and therefore magnification produced by the objective lens can be of 70, 80, 100 times. This FO is very small, which gives L upon FO. L upon FO, it becomes a very large number. Since it's a very large number, we can remove this one, and VO upon UO can be approximated with what? Minus of L upon FO. Just remember that FO is much smaller than the lens separation. Now, you have got your VO upon UO, which is MO. Put this value of VO upon UO in case 2 and case 1, and you get your total magnification. Total magnification, you can see, is coming what? Negative. Negative means what? The original object and final image. Final image is an inverted image with respect to the original object, and therefore total magnification in this case is coming what? Negative. Now, this is the simple working formula and all. There are a few things which you need to remember. If you want that a real image forms with the help of the objective lens, then this UO should be first of all greater than FO. If you place an object at a position which is less than FO, you will get what? Virtual image, which is happening in this case. You're getting a virtual image. This distance is less than Fe. But for an objective lens, since we are interested in a real image, we say that this UO mod of UO should be greater than FO. Now, once I say that mod UO is greater than FO, you don't want to place this object at infinity or at very large distance. If you place this object very large distance, then this image will fall at the focus of the eyepiece, objective lens. And our aim is to form this object, which is the intermediate image, object for this, the intermediate image, as close to the eyepiece as possible. And therefore, we keep mod of UO very close to FO. Very close to what? FO, but beyond the focal plane. Not before, after. Remember this point. Note down everything.